right, now let's try one more variation of this problem of finding dose at a different point. Um, we're going to have again a phantom or a patient, and we've got a beam on here. This is beam is 100 centimeters to this point, which is at the midpoint. So this is an SAD type beam. We'll say this patient or phantom is 20 centimeters thick. This point is 10 centimeters deep in the patient, so in other words, it's at midline. And now we're going to look at another point that's 15 centimeters deep instead of 10, and we are going to say at this point we want to find the dose there. I guess I should tell you the dose at this one. So the dose here, like before, is 180 centigrade, and we want to find the dose at that point, giving this information. Of course, I also have to give you a TMR table. In this case, and of course, when you're doing this on a test or a problem, you're going to have a bigger table. I'm really just giving you the two numbers you're going to need. The table you would have on a problem might have different field sizes and different depths, but I'm going to assume that this is just the field size we want and the depths we want, these two numbers here. So given this, how would you go about doing this problem? One thing I should mention here is the first thing I always tell people to do is to make a guess at the problem. In this case, just guess, is this answer going to be more or less than 180 centigrade? So in this case, we have a beam that's coming from this direction. This point is deeper in the patient, so it's going to have more attenuation. It's also farther away, so it's going to, which accounts for inverse squared. It's going to go down by inverse squared as well. So we would assume that this point, whatever the answer is going to be less than 180 centigrade. And so that's important. Sometimes a lot of these, the way we get at these answers is to do a ratio, and it's easy to mix your ratio up. In other words, have the top on the bottom on the top, whatever. And so it's always good to know ahead of time what you're expecting the answer to be. We're expecting it to be less than 180 centigrade. All right, to solve this problem, we're going to again look at the definition of the tissue maximum ratio. And let's assume we have three phantoms here, and we look at a line that is at equal distance across here. And I'm going to put 3 points along this line, one in each phantom. Draw this out here. So this point here is at a depth d1. This point here is at a depth d max, and this point here is at a depth d2. And we're going to place identical beams on each of these phantoms. So these beams are each at an identical distance to each point, and they're the same field size, same energy, and everything. The only difference is their depths in the phantom. So we have write some equation here. We have two equations here. I'm going to call it TMR1, TMR2. TMR1 is the dose at this depth here, D1, divided by the dose over here at the Dmax depth. That would be the definition of TMR based on these 2 points. TMR2 is similar. It's just the dose over here at point 2, the dose at point 2, divided by the dose at Dmax. So we can use the same Dmax in each case because they're all at the same, they all have the same field size, they're at the same distance from the source. So these two Dmaxes are the same. We just have the dose at point 2 here, the dose at point 1 here. And this is how I'm going to, this is the first step in getting to a relationship between dose at these 2 points. I have a dose at one depth and a dose at another depth, and I have a TMR table. Now this won't, I can't just take, again, can't just take the ratio of TMRs alone, because TMR would mean they're at the same distance from the source, which these are not. However, this would be the first step. So here I'd have them at the same distance from the source, but I could at least look at the get the relationship of one dose to another just based on their depths. So let me write both equations up top here. So I have TMR 2 is equal to the dose at 2 divided by d max, and TMR 1 is equal to the dose at 1 divided by d max. I've put them under a made them as a fraction here, so I can cancel the d maxes because they're the same point. And what I'm going to be left here with here is going to be TMR2 over TMR1 is equal to the dose at point 2 over the dose at point 1. So in this case, if I wanted to solve for the dose at point 2, let me write it down here in the bottom. I could say the dose at point 2 is equal to the dose at point 1, putting this on the other side of the equation, times the ratio of the TMRs. TMR 2 over TMR1. And again, getting back to our expectation that we're expecting this dose to be less than that dose. This is where I said it's good to know what you're expecting, because here, of course, we have the TMR at 10 centimeters is 0.778, at 15 is 0.696. Go back to our equation here. This TMR2 is less than the TMR1, which is what we'd expect. We'd expect this ratio to be less than 1 because we're going to, the dose at point 2 is going to be less than the dose at point 1. Now in this case it's at the same distance, but the dose here, the beam here is going through more tissue or more phantom, so we'd expect this dose to be less. So that's where that knowing what you're expecting helps out. Alright, so here's the equation we just derived, that the dose at point 2 is equal to the dose at point 1 by the ratio of the TMRs. So let's just put in our numbers here. It's 180 centigrade times 0.696 divided by 0.778. I'll bring up my calculator again. So we have 180 times 0.696 divided by 0.778, and that equals 161, let's just call it 161 even. So this is equal to 161 centigrade. However, we are not done yet, because all we really have found out is the difference in dose between here and here if we were at the same distance from the source. But of course we're not at the same distance from the source. This point is farther away, and so we're going to have to use, again, inverse squared to go from here to here. Again, what are we going to expect? We got an answer of 161 centigrade. We're going to move a little bit farther away, so we're going to expect this answer to go down a little bit because of inverse squared. So what is our inverse squared factor going to be? Well, this point here is 100 centimeters from the source. It's an SAD treatment. And what is, how far is this source away? Well, if it's 10 centimeters depth to here, and it's 15 to here, the difference here is 5 cm. So the distance from here to here is 100 centimeters down to 105. Now this would be a easy place to make a mistake, to assume maybe this, because this is 15 centimeters depth, that this distance we're going to use is 115. But it's not. It's only the difference between this point and that point. So it's only 5 centimeters farther. So the distance from to this one is 105 centimeters. So let's write that here. So we have the inverse squared factor is just going from 100 to 105 squared. Let's bring up our calculator again. 100 divided by 105, and we're going to square it. We get 0.907. I'll just write that here. There you go, 0.907. Again, if we're keep in mind that we expected this to be less than 1, which it is. If we'd gotten an answer that was greater than 1, we know we did this backwards. And now our final answer is just going to be these two multiplied together, 0.907 times 161. We still got that up, times 161. And our final answer is 146 centigrade. So that would be our final answer, 146 centigrade to this point, using just the TMRs. So the main point about TMRs is that they're not hard to use, and we can use them like a ratio, like we did with percent depth dose. The only difference is that the ratio just gives you the difference in doses if you were at that same point, at that same distance from the source. Of course, we're not, so we also have to take inverse squared into account.